Today I will overview the basic concepts presented in Unit 11, the Thermochemistry unit. First, revisiting basic energy definitions. Energy, heat, thermal energy, temperature. These are ideas that we've already covered, and it's important to understand the distinction between those. Again, a reminder about heat. Heat flows from warmer objects to cooler objects. In the discussion for this class, this is a physical process where particles actually bump into each other. So faster moving particles collide with and speed up slower moving particles in another substance or within the same substance. This is an overview of the units of energy. Notice that it shows that energy has different possible units. The standard SI unit is the joule. So much of calorimetry and heat is also linked to this idea of a calorie, which is a unit of energy, a unit of heat, if you will. The idea of energy in food is linked to calories. And there's a distinction between the capital C calories and the lowercase letter c calories that we need to make sure that we pay attention to. We probably remember from physics that energy can be converted from one form to another. And in this simple case, the potential energy at the top of the hill can be converted to other forms of energy at the bottom of the hill, such as kinetic energy. One of the overriding principles that applies is the first law of thermodynamics. The first law of thermodynamics is a fancy way of discussing or expressing a law of conservation of energy, and that is that the energy is neither created nor destroyed. If we think about the universe, the place where we live, the Earth, the solar system, our galaxy, everything, the total energy content of the universe is constant. And therefore, we're just swapping one form of energy within that different parts compared to others. This leads us to a necessary definition of system and surroundings. If I refer to the system is the molecules or particles that I want to study. And the surroundings are things which are not those. So for example, if there's a reaction between hydrogen and oxygen to form water, the system is just going to be the actual atoms of hydrogen and oxygen. They become water, they're rearranged, but it does not include anything separate from that. And therefore, in this case, the piston, the cylinder, the metal, the building that has the piston and the cylinder, these are all considered to be the surroundings. The main type of energy we discuss in chemistry is enthalpy. And enthalpy refers to the energy content of a substance. And you could think of it as an energy. Energy is a more generic term. It's not potential energy. It's not just kinetic energy. It's a term that is unique to chemistry that is super helpful to describe, used to describe the energy associated with chemical processes. There's some pretty important math that we could go into that's not necessary, but there's a derivation that proves that the change in enthalpy of a system, again, what we're examining, is equal to the heat flow of the system. And therefore, if I change the heat flow, then I'm also changing the enthalpy. This is a constant pressure. In this course, I won't ask you to consider non-constant pressure scenarios, but this relationship only applies at constant pressure. It's important if we're talking about the exchange of heat or changes in heat that we describe processes which are endothermic and exothermic. If in a system heat is absorbed, then that means that the change in enthalpy of the system is positive. Exothermic the heat is released by the system. Therefore, the delta H is negative. Notice that this is all dependent upon how I define the term system. And notice that if delta H is positive for a system, that means that delta H is negative for the surroundings near that system. And the reverse is true for an exothermic process. This leads us to the most important conclusion that we want here, and that is that I want to talk about the change in enthalpy of a reaction, otherwise known as the heat of reaction. In this reaction, notice that before I have hydrogen and oxygen molecules, and notice that afterwards I've created water molecules. This energy diagram over here shows that before the reaction, the particles have higher energy, higher enthalpy than afterwards. And this schematic, which is merely symbolic, but shows us visually the relationship between enthalpy before and after, shows that the enthalpy started high and went low. Therefore, the change in enthalpy for those atoms is negative. Another way of thinking about it is the change in enthalpy before the reaction. Okay, this is the combustion reaction between methane and oxygen. Notice that enthalpy is greater than that of the product, right? So I could determine the delta H by taking the enthalpy of the products and subtracting the enthalpy of the reactants. In other words, a smaller number minus a bigger number gives me a negative number. Another way to visualize that is a reaction progress graph. Notice that the reactants, in the case on the left here of an endothermic reaction, have a lower energy than that of the products. And the difference between those two is the delta H. In the case of an exothermic reaction, notice that the reactants are greater than the products, and therefore it lowers over the course of the reaction. It's interesting to note that this extra hump here is referred to as the activation energy. We're not going to talk about that necessarily in this class, but the activation energy is what prevents reactants from becoming products all the time. In other words, in order to get methane to react with oxygen, I need to light a match, and that match actually pushes the initial reactants over this hump to become products. And therefore, I need something to get over that hump in order for this reaction to proceed. A couple of final notes here about enthalpy. Enthalpy is an extensive property. Extensive property means that it depends upon the quantity. If I decide to write the reaction in reverse, that just changes the sign of the reaction. And the change in enthalpy of a reaction depends upon the state of the substance. In other words, if I react carbon dioxide as a gas, that's going to have a different enthalpy than if I react carbon dioxide as a solid. And carbon dioxide as a solid is, as you know, dry ice. So conducting a reaction with different states matters. So I have to pay attention to the state. If we revisit this idea of heat capacity, again, heat capacity is the energy needed to change temperature. And as we've discussed already in this class, different substances have different specific heat capacities or heat capacity. Notice that water is the highest out of all of these. And notice that mercury is the lowest. You're going to see these different terms here: specific heat capacity, specific heat, and heat capacity. They probably refer to the same idea. In other words, there are some technical differences between how I express that for the purposes of this class. And in most textbooks and videos, they use these terms interchangeably. And notice that this diagram over here says that if I have water at 14.5 degrees, and I take it to water at 15.5 degrees. By the way, this is liquid water. It requires 4.184 joules, or 1 calorie, to make that happen. The final couple of slides are related to calorimetry. Notice that the purpose of a calorimeter is to isolate the system, whatever's going on inside here, with outside of the system, right? So calorimetry is a way that I can use this to measure something. The idea of the calorimeter is the fact that since the inside is isolated from the outside, processes can exchange energy inside. In the case of this reaction here, we could have a reaction happening that has a delta H, and any change in reaction is going to produce a change in the heat flow of the water. And since water is easily measured with this thermometer, and Q equals MC delta T, I can use that to determine delta H information. And then we come here to the calorimetry big ideas. We can predict delta T from delta H over reaction. That means that if there's a reaction that gives off heat, I know that the temperature of the water surrounding it is going to go up. We can relate delta H to delta heat specifically using equations. Water is the vehicle that reflects this energy change, and I can never measure delta H directly. In other words, if I want to measure this enthalpy change, I have to measure its impact on the water, which is going to be inside the calorimeter.